So let's start today's lecture. So today's lecture is, let me find it here. Okay. We are beginning today a second unit, which is quantization of charge, light, and energy. So this is, when I was preparing it, I saw that I think I will do today only quantization of charge, and I wanted to go on after quantization of charge to the nuclear atom, but as we well, it's the syllabus is written this way, so next time we will see the quantization of light, particularly the blackbody radiation and the Compton effect and photoelectric effect, okay? And after that, we will have all the discoveries on the structure of the atoms. Okay, that followed actually what we will see today, quantization of charge and of energy, okay? So we have 4 parts: quantization of electric charge, blackbody radiation, photoelectric effect, and X-rays and Compton effect. Okay, so only to begin, it is modern physics. We have to say what is modern, what is old, and particularly our this topic, their topic, the physics of the 20th century. And so we have this notion that the matter, okay, was constituted of particles, okay, and they were called atoms, which in Greek means it's a negative, so it is not, and tom is to cut, so you cannot cut these particles. They are the ultimate constituents of matter, which is we know it's not true, but it's some kind of it's a constituent which has some properties, okay, sufficient to we will not look inside. We will look inside because we are going to look at the electrons, okay, electrons and all which is not electrons in the atoms, okay. So this is quite old, for 450 before Christ, Democritus, okay, but without any experimental evidence, obviously. So we have some timeline here of all the things, the discoveries which are important, okay, in this quantization of matter and of charge, okay. So at the beginning of the 11th century, Avogadro made a series of experiments, and he discovered that all gases, okay, at a given temperature, they all contain the same number, okay, of number of particles and per unit volume, okay. And this is something, and we know that this, okay, for example, okay, we will have this is the number of Avogadro, okay, we will use it after, which is of the order of 10 to the 23 atoms or particles, okay, for one, what you call quantity, okay, of 1 mole, okay. And after that, we have the very important discoveries by Robert Brown. He was a botanist, and he observed with his microscope the movement of tiny pollen, okay, grains of pollen, and they seem to have some very interesting movement. And so this is called the Brownian motion. And this was later, I won't, enter into details here, but I put three names here, Bachelier, Einstein, and Perrin. So Bachelier, I think he was a student of Henri Poincaré, and he described this motion as statistically, stochastically, And Einstein in 1905, which it is one of his three important work he published in 1905. He explained this Brownian motion as resulting from the collisions of these macroscopic pollen grains with the molecules of water, in which this pollen was in suspension. And Perrin, a few years after Einstein, he demonstrated experimentally that the theory of Einstein was correct. So I think that Perrin won the Nobel Prize for this interesting feat, And so 1833 we have Faraday. So his name is associated with a lot of concept in physics and laws, and this is here the law of electrolysis. He was studying the electric properties of solutions with electrolytes inside, so ions basically. And so he wrote this law. There is a number, constant actually, a constant of Faraday, which is called F. I think this is the constant of Faraday. And he measured this constant. It is the charge per mole of elementary charge. So he saw there was a relationship between the quantity of ions, basically, and the electricity, and this quantity F, which is the number of the constant of Avogadro times the elementary charge, is 96,000, something like that. So it was also a step towards the quantization of charge. Nothing was really clear, but Faraday had this rule. 1869, Mendeleev. It's very important also, periodic table of the elements, because this is initially something to put order in all the known elements at the time, depending on their properties. And so, you have the lines where you have actually the atomic number increasing, and you have the columns, where you have some properties which are similar. And there was also some places where there were no elements, and so they were expected to be discovered later, and they were, Jean Perrin again, but sooner, It's because this one here, when he experimentally demonstrated, proved, the theory of Einstein was right. It was at the beginning of the 20th century. Here we have at the end of the 19th century, he showed that the charge of cathodic rays were negative. So he could show that. I will explain now what is a cathode ray, and he measured the sign of this charge. It was negative. So cathode ray is something scientists at the time were very interested in, and actually it's an electronic beam. It's a beam of electrons, and so we show it was negative. Actually, obviously, it's a convention, to say it's negative or positive, In 1897, J.J. Thomson. Here I put his name because J.J. Thomson discovered the electron, and I think it as a particle, and we will see later that his son, which is also a Thomson, I don't remember his name, he discovered the electron as a wave, okay? And so I will stop this part of quantization of electric charge here with Millikan at the beginning of the 19th century, at the 20th century, when the Thomson measured the ratio charge over the mass of the electron, and Millikan he measured the value of the elementary charge of the electron E. Okay. So first, I have to speak about what is a cathode ray. So we will see this kind of experimental arrangement. You have here some recipient. It's a glass one. You have to you can watch through it, okay? And so you have here the cathode. This is the anode. So you can see the cathode is the two electrodes, okay? C and A. C is polarized minus and A is polarized plus. And so you establish a potential difference, okay? The tension between these two cathodes. B is a slit, okay? And you have here, but it's for now it's not important. What is the cathode ray? So this is an electron beam, which is at the beginning it was a cold cathode. Okay, so they had to put a very high voltage between the cathode and the anode, and the cathode ray is called this way because it was as if it were emitted by the cathode. Okay, actually what happened is that they managed to ionize some traces of gas which were in this evacuated recipient. Okay, and so they had ions, so they ionized them, and the electrons were accelerated here through this electric field, and so you can see the glass glowing at the end, okay, at of this arrangement here. So they didn't know what it was, and they called it cathode rays, okay? And so what is being used now, and already maybe at the time of the experiment of Thomson, this is fermionic emission. So instead of a solid cathode, you have a filament, okay? So you have some electric current passing through the filament, and the filament will emit electrons, and these electrons are accelerated by the potential difference between anode and cathode, and so you manage to have a beam, okay, of electrons. Okay, so this is cathode rays. So what did J.J. Thomson do with this arrangement here? So simply what he did was put, if you don't have these plates, electric plates D and E here, so your ray of electrons will go directly, okay, to the end of this the bulb, okay. So this is evacuated. You don't have gas inside, okay. You only have these electrons, and they are accelerated, and you see here where they collide with the surface. And this is, you can put some material which will be phosphorescent under the action. Okay, actually this is what used to be done when we use some oscilloscopes, okay, or which were this was, okay, an electron beam, and you put some some material here to visualize better, okay, where the electrons will collide here. So if you don't put any electric field between these plates, so they will go, you will have some regular, okay, trace here. And so he put some electric field between them, and so as the electrons are charged particles, they will be deviated by the electric field. And so this way, for example, if you put plus here, minus here, so the electric field is in this direction, and the electrons are negatively charged, so there will be the deviation will be upward, okay? And so we can control the amplitude of this electric field. I wrote it like this. E, this is the electric field between the two plates, and this is the potential difference between the two of them, okay? So you control that because this is, you are applying it between them, and D is the distance between them, okay? So you have this one, so you know exactly what is the value of this electric field, and you know that you applied the second law of Newton, and you have that the force, the Coulomb force, is equal to the mass, and this is the mass of the electrons, because these particles are electrons, times, okay, the acceleration. And obviously everything happens here in the vertical direction, so I called it y, and the horizontal direction I called it x, okay? So this is the second derivative of y, okay, which is the position, the vertical position of the electrons, okay, relative to time, okay? So you have the velocity is constant on the horizontal axis, okay, because you have no force applied, okay? So the velocity here will be the same as the velocity at the entry, okay, before entering the field between the plates. And the velocity of on the vertical velocity, Vy, will be, okay, you see this acceleration is constant, okay? The acceleration here is the charge divided by the mass times the electric field. If the electric field is constant, so is the acceleration, okay? And so you have this relation, the velocity, and here the time. What time is that? We are interested how this is better to understand what happens. So you have x and you have y. Actually, what I wrote here, I wrote L, okay, which is the dimension, the horizontal dimension here. This is an axis. And so I called, when it enters, this is 0, and when it exits, okay, the field, it is L, okay? This is the length of the plates, and Y is the shift, okay, of the beam in the vertical direction, okay? And so we have here Y, this one, at the exit of the field, okay? And so this Y, I will call it YP, okay? So this is YP, okay? So we write it this way. So you have the charge over the mass, okay? This is the potential difference, the distance between the plates. And here, this is L, the length of the plates. And you have here the velocity V naught, okay? Which is the velocity acquired by the electrons before, okay? Actually, the velocity they acquire when accelerated between the cathode and the anode, okay? So after that, they are not subjected to any electric field. So this velocity from A to the screen is V naught, okay, constant. And so the only difficulty here, okay, so you see we have some way of determining the ratio of the charge over the mass, okay, because everything, this can be measured, okay, we know it, we know everything. All we have to know is the velocity V naught, okay? So actually you can say, well, maybe we can know it from this electric field, but I think you don't know what is the velocity of the electrons when they are ejected from the cathode. Okay, so there is a very easy way to measure this V0, V naught. Do you have any idea how it can be done? You use a magnetic field. So if you remember what a magnetic field does on a charged particle with velocity v, what does it do? You have the force, okay, magnetic force, okay, which will be something like the charge times the velocity, okay. And here you have P, okay. And so, if you have some velocity here, which is our case, V0, you put some magnetic field, okay, in the plane, in the horizontal plane, perpendicular to the velocity and to the electric field. So your particle will be having some movement, okay. So depending here, let me see, VB, right hand, okay, VB. So it will be deviated to. So I should put it the other way. Okay, B is coming here, so you will have some, okay, you will shift downward, okay, the particle of the the trajectory of the particle. So you have your magnetic field this way, B, you have your electric field this way, and this electric field will do that. And so you can adjust, okay, whatever you want, okay, electric field, magnetic field, so that you will have the electronic beam, the cathode ray, okay, going to the screen, okay, without being deviated. So when you obtain this, you know what? That the electric force, okay, upward equal magnetic force downward, and so you have E. I just put the charge, elementary charge, okay, which is what I used to call Q, but this is the electronic charge, okay, elementary charge, E equal to E V, here is 0, B, okay, and so here you know E, you know V, no, you don't know, okay, you have that your velocity is the electric field over the magnetic field, okay, so you can substitute here with this one, and so you will have yp equal to E over M to M. Here you have field. Where is it? QE over M, QE over M. Times, no. This is not correct, right? Okay, this is not correct because the acceleration is Q over ME, but here we have T square, yeah? So this is T square. Okay, so I want to write it because Q, this is L over V0, L over V0 square, this is E over M, and here I will put the mass of the electron, L square over V0, E square. Okay, and so what you can measure with this apparatus, this is not E because you don't know. What you know is B, you know L, you know E, okay? But you don't know this quantity here, okay? So you can measure it, and this is what Thomson did, okay? Equal to YP over YP over P. Okay, something like that. Actually, I will probably give you an exercise to have some ideas about the orders of magnitudes, okay, of what you can measure. Because after you are here, you won't measure here, okay? It's very difficult to measure. But if you have a screen here, so you can, this would be 0. Actually, yeah. Actually, I won't write it with B and E because this is V0, okay? This is V0. And you measure V0, okay? And so you can put it and, okay. As a function of YP, L, E, V0, okay? And so this is not really as a function of YP that you do that. You will measure, okay? You will measure this distance here, Y, okay? And so you know, okay, the distance here, I can put it, okay, I can call it delta L, for example. And so you have an additional distance where the electrons are not submitted to any force, and so they will go in with a constant velocity that you know, okay? And so you measure the distance here, and you can measure the ratio E over M, okay? So what Thomson measured E over M, I wrote it here. Okay, numerical value, this is 1.7588, 10 to the 11, okay, and the unit is Coulomb. per, okay, coulomb per kilogram, okay. So this is something very nice, okay. If we look, let me show you here. Constant in units. No. Sorry. Here, okay. Okay, so you have here this this list, okay. I took it from the NIST, okay. And so you remember we have, this is after May 20 should be, okay. I think this is after May 2019, and you have here exact values. Yes, exact. So what we have here is the elementary charge, but let's say we don't know it. We have also the electron mass, we don't know it, but you have the ratio of electron charge to mass quotient, okay, minus E, because this is negative. And you have here up to 75.88, this is the same. So after that you have 20 something, okay. And so this is a very good measurement actually. I think I will. No. Sorry, this thing is not very nice. Okay. Okay, back here. Currently, what we have, current value E over M. Okay, E 1. Okay, 8, and here this is 20 something. Let me see. Okay, so this is very important to remember how this was done, because you all are students of engineering courses. So for you have electrons, okay, you use them, electric and electronic engineering. So this is something you use them every day, but it was not obvious, okay, at that time. And so very few things were known about the structure of the matter, okay. So there are atoms, okay. The chemistry was very important to determine that there were some atoms, some things that you could combine to do molecules, and they had some chemical properties. You can do reactions and things like that. But exactly how it was organized at the microscopic level was impossible to see, okay, at that time. Still isn't very easy. And so you have to deduce everything from indirect measurements. And so this is the measurement from Thomson, and this is what he had. But he couldn't. The other thing he noticed that because in this apparatus, actually he can deflect things heavier, okay, heavier ions, or ions, for example, negative ions, okay. So for example, a very simple atom when you ionize it, so it has a mass. Okay, we now know that, for example, the smallest one would be hydrogen, and so you could see that this mass of these cathode particles were very, very small. Okay, it was much smaller than the mass of the smallest ion. Okay, and we know that the mass of the electron is something like 2000, okay, smaller than the mass of the proton. Okay, if you ionize an hydrogen atom, okay, so you will have a proton, and the mass of the electron is 1800 and something, okay, smaller than the mass of the proton. Okay, so he could see it, but he couldn't measure it. Okay, so who could measure, okay, separately, okay, the elementary charge, okay, from the mass. Okay, all we had was this ratio. Okay, it was Millikan. Okay, so Millikan is a name also which is associated with this discovery of the electrons. Okay, and so what he did, he began a series of experiments in 1906, but it took a few years to have good measurements. And the apparatus he uses is this one. You have some closed space, okay, and you have two plates, okay. Between these two plates, you can okay, put some electric field. Okay, you have two electrodes actually, and so this one is as a whole, and you can vaporize some oil, okay, through it, and so the oil will, as it falls, okay, inside this chamber, it will take some charges, okay, elementary charges, but it's not, you don't have one or two. You don't know exactly how many you have. How do you know that this oil is charged? Okay, this is because you see the behavior of this oil drops, okay, between the two plates, okay, between the two electrodes, and so you can play, okay, with the movement, okay, of the drops by modulating the electric field between the plates. And so, for example, if you have negative, okay, charges, which is the case, okay, you have electrons, you will have some, you know the direction of your electric field, and so you can, you have a drop of oil with, I don't know if it's negative. Let's say it is. Okay, you have some, yes it is. You have some charges, okay? And so this is a big one, okay? It's macroscopic. You can see, okay? You have a telescope. You have to illuminate, okay, the whole scenery to watch really what happens with your oil drop. And so you know that this is, okay, I will apply the second law of Newton, as always. So this is very classical experiment, okay, very classical explanation, but the discovery has profound consequences of the physics thereafter, okay, the physics of the 20th century, but it's completely classical, okay. And so you have here the mass, okay, of your drop times the acceleration of gravity, and so you can put something here, for example, you can equilibrate, okay, you can have your drop, okay, not falling, okay, under the gravitational force, okay. So you have the number of charge here. I will call it Q, okay, Q times electric field, okay. And so you can have this quantity equal to this one, and so you know that you have some you can write QE equal mg, okay. The problem, you don't know necessarily the mass of your drop, okay, but the experiment is this one. We don't have a kit, we don't have this experiment in our institution, but I remember having done this experiment, okay, with in the modern physics laboratory. And so you can watch the droplets. And so what do you measure? What you measure is this one. So first you cut your electric field, okay, E equal to 0, and all what you will measure, you know the distance here between plates, let's call it D, okay, and so you will measure the time, time of fall, okay, so you have to follow a given oil drop, okay. And so this time will be the distance, which is t, okay. Or you can have something better, okay. You can measure this distance, okay, quite precisely. G over the velocity of fall. So you will say that this velocity should be varying, yes, because you have force if you cut this one. So you are not saying anything, but the fact is you don't have only this one and you won't have only this one. Why? Because it is not evacuated, okay? This is not the same thing as here in the Thomson experiment when you have you don't have a gas here. Here you have air, essentially. And so you will have the forces of friction, okay, with air. And so actually what you have is, I will take it and do it again, okay? So any idea? You remember from mechanics, the first semester of basic physics, we saw what when you have some friction, okay, with the medium, okay, where the movement is being done, you can reach a limit velocity, okay, and so this is what happens typically. So I will draw again, okay. You have your oil drop, you have no electric field, so what are the forces? So you have here the mass, okay, the weight, okay, of and you have the velocity. You reach a constant velocity, okay, because this force is this. I can write it this way. Initially, the force is very small, okay. You have friction force, okay. I can call it F, for example, F friction force, okay. And so For small velocities, we can write that F, the modulus of this force, is proportional to the velocity, okay? And so you will have a coefficient here, I will call it beta, okay? And so you have here mg, okay? And here you have the friction force, and as the velocity increases, okay, because you have the acceleration downward, and so will your force, okay, until it reaches, okay, the same value, and so you will have constant velocity for beta v equal mg, okay? So what is the falling time? Falling time T4 will be the distance, I called it T over V, okay? And V, I don't know if you know beta, we will see if we need it, okay? But essentially you will derive, okay, this one you don't know. But okay, you know the velocity actually because you measure this, okay, so it's okay. And so what you do after that is you switch on E, okay, electric field. And so now what you have, so you see it's application of the second law of Newton. So you will always have your weight here, downward, okay? But now what you are doing is you will have electric force QE, and you will have beta V, okay? And this is mg. And so you will have T rise. Okay, so you watch the drop going up. Okay, so you can put an electric field so that it is stronger. Okay, then that's not true. It is rising, so this one is downward also. Okay, beta V. Okay, so T rise equal same D over V rise. Okay, and so okay, so you have you will have that. And by measuring this one, okay, so you will have QE, okay, constant velocity. You will have QE equal to beta V rise plus. And so you can write V rise as a function of this one. And so you will compute the difference between the rising time minus falling time, okay? And so I can write it down, just let me a minute. Actually, what you know, it's not the difference. What you want to measure, okay, this is the charge. So you will have the charge, okay, which is not the charge. Let me see if this is the same. Okay, so you will have Q, which is an integer number of the elementary charge, okay, which will be a function of T rise, T fall, okay. And so you can do it for, you do it for 1, you do it for 2 drops, etc. And so you will see that you will have n and you will have other values of n, but they all will be, okay, so you can have n, you can have n plus 1, n plus 2, okay? And so you can measure it. I will put it as an exercise also, okay? So, so what we saw with these two very important experiments, okay? Experiments of the beginning of the end of the 19th, beginning of the 20th century, is actually the discovery of the electron. So let me see here what the kind of value he obtained. I think it's important here. Let me take it. What he measured was these two values, okay? So, 1 point blah 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 10 to the 19, okay? Coulomb for the elementary charge, and here 9.11, okay, blah blah, 10 to the minus. This is minus, okay? And if we look at the current values for this, okay, I closed it. Sorry. I don't have it anymore. I don't know why. Okay, I will copy paste. E, elementary charge. Elementary charge here. Okay, so the elementary charge. Okay, you remember that now the elementary charge is not. This is an exact quantity. Okay, you don't have to measure it. Okay, you know the value. Okay, you can measure it to measure something else, but the value of the elementary charge is this one. Okay, so for what we use in general, it is very good. Okay, until set. Okay, he had it. And the mass of the electron. Once you know the charge, you know the mass, because Thomson had measured the ratio. Okay, so you know the value of the ratio. So if you know the mass, you can have a value of the mass. If you know the charge, you can have a value of the mass here. Okay, electron mass 9 point. Okay, so this is, so you can see that these are very, it's not high technology, okay, but they made very, very, very careful measurement, and they arrived at values which are really impressive, okay, the measurements of the elementary charge and the electron, okay. So I will stop here, because next time I want us to study the quantization of light and energy, and so this is a very closed subject. I cannot begin with the Compton or photoelectric effect, okay, and so the black body radiation, okay, this will be the first topic next time, and I will send you a list, okay, so you can train on this first experimental discoveries, okay, of the quantization of matter.